Chapter 14 covers the chemistry of conjugated unsaturated systems, and in this video we'll describe what a conjugated system is, we'll look at the stability of conjugated systems, and we'll also examine kinetic versus thermodynamic control and electrophilic addition to conjugated dienes. The word conjugated means coupled or connected, and in the context of chemistry, the things that are connected are pi systems, such as double bonds, triple bonds, and benzene rings. Conjugated systems have pi bond functionality separated by a single covalent bond. As you can see here, you have two carbon-carbon double bonds in this diene separated by a single bond. Here are some examples of other conjugated systems that include structural features other than carbon-carbon double bonds that have pi bonds in them. All conjugated systems have a contiguous array of connected p orbitals, atoms that have p orbitals in the conjugated system. And non-conjugated systems have pi systems which are isolated from each other. In general, conjugated pi systems are more stable than isolated pi systems, most likely due to partial delocalization of pi electrons through the entire conjugated pi orbital system. There is some evidence, experimental evidence, to suggest this. Take a look at 1-butene. It can be hydrogenated to butane, and in that process 30.4 kcals per mole of energy is released, and that can be measured experimentally. For 1,4-pentadiene, a system that has two double bonds, you would expect that, well, if there's two double bonds, you would have twice the amount of energy released upon catalytic hydrogenation of both of those double bonds, and experiment shows that that's the case, 60.8 kcals per mole. However, compare this isolated system to a conjugated system, 1,3-butadiene. This still has two double bonds, just like 1,4-pentadiene. However, only 57.1 kcals per mole of energy is released. This difference of 3.7 kcals per mole is accounted for by partial delocalization of the pi electrons along this pi framework. Let's turn to some chemistry of conjugated systems. You might think that in all chemical reactions, the most stable product, the product that's lowest in energy, would always be the major product in that chemical reaction, but that's not always the case. In reversible, that is equilibrium reactions, that can lead to different products by competing pathways, the product that's formed the fastest, also referred to as the kinetic product, is not always the most stable product, sometimes referred to as the thermodynamic product. And it's possible to, in some cases, to choose reaction conditions that could lead to the kinetic product being the major product or the thermodynamic product being the major product. Let's look at the possible reaction pathways for electrophilic addition to a conjugated diene. First, the electrophile would approach the diene and be attracted to its pi electrons and bind itself to either carbons 1 or 2. We know it's not going to bind to carbon number 2 because you would end up with a primary carbocation. So once we attach it to carbon number 1, we end up with this carbocation, an allylic carbocation, which of course has another resonance structure. Notice that resonance structure 1 has the positive charge on a secondary carbon, but resonance structure 2 has the positive charge on a primary carbon. Both of these resonance structures contribute to the overall electronic picture of this molecule, but because of the fact that in resonance structure 1, the positive charge is on a secondary carbon versus a primary carbon in number 2, structure number 1 contributes more. What does that mean? It means that if we can actually look at this molecule with our eyes and see the atoms and electrons and see exactly where they are, we would see a higher concentration of electrons around this primary carbon and a smaller concentration of electrons congregating around this secondary carbon. And that's because, as you know already, primary carbons have a much more tougher time to accept a positive charge than a secondary carbon, which means that the electrons are going to be pulled more toward the primary carbon than the secondary carbon. So there's more positive charge on this carbon than there is on that carbon. Nonetheless, a nucleophile could attack either position. Both of these positions are electrophilic, and upon nucleophilic attack at carbon number 2, we end up with the product of 1,2 addition. When the nucleophile attacks carbon number 4, we end up with the product of 1,4 addition. So we have two possible addition products in this case. What affects or controls the product ratio? You'll see that the substitution pattern on the diene system and also the temperature at which you run the reaction is going to have great effect on whether the kinetic or the thermodynamic product is the major product. All right, let's look at a real chemical reaction, electrophilic addition of HBr to 1,3-butadiene. And you have two possible products that could be afforded, the 1,2 product or the 1,4 product. Now, which of these two do you think would be the thermodynamic product, the most stable product? We can gauge that by looking at the bond energies involved in the formation of the 1,2 versus the 1,4 product. Well, let's first start with the 1,2 product. Take a look at the type of bond it has here. It has a bond between a secondary carbon and bromine. In the 1,4 product, we have a primary carbon attached to bromine. The secondary carbon-bromine bond is weaker than the primary carbon-bromine bond. Why is that? Well, if you broke this bond and Br took the electrons with it and it left as bromide, you would end up with a secondary cation here. If you broke this bond heterolytically and Br takes the electrons and you get bromide leaving, you get a primary carbocation. Therefore, this bond is a stronger bond. As this bond's breaking, this carbon doesn't want to have a positive charge, so it's really tugging at these electrons more strongly than the secondary carbon. It's easier to form a secondary carbocation than a primary carbocation, which makes this bond weaker by a kcal or so. All right. What's another difference between the 1,2 and the 1,4? The 1,2 product has a monosubstituted double bond. The 1,4 product has a disubstituted double bond. When you were studying alkenes, you learned that the more substituents on a double bond, the lower in energy it is, the more stable it is. So the 1,4 product has two things going for it. It has a stronger carbon-bromine bond, and it also has a more substituted double bond. So overall, you would say that the 1,4 product is the thermodynamic product, the more stable product. When you run this reaction in the laboratory, you might think that this would always be the major product formed. But when you do it at different temperatures, you end up at low temperature, minus 78 degrees, very low, getting 90% of the 1,2 product, the less stable product. But when you allow the system to come to equilibrium by heating it to a higher temperature, you actually do get the 1,4 product, the thermodynamic product, as the major product. So the question is, why is it that at low temperature you get this 1,2 product, the so-called kinetic product? Why does it form faster than the 1,4 product? And the key thing here is that you're not allowing the system to come to equilibrium. You're not allowing the reaction to go to equilibrium when you keep the temperature so low. All right, but why is it that this forms faster than the 1,4 product? Why couldn't, in this case, the 1,4 product be both the kinetic and the thermodynamic product? Well, the reason that this forms faster than the 1,4 product, well, there's two possible reasons. Look at this carbocation, the one that would lead to the 1,2 product. It has a secondary carbocation. The 1,4 product would have to come from the other resonance structure. the allylic carbocation with the primary carbon having the positive charge. We said on the previous slide that this is a major resonance contributor. There's less electron density around the secondary carbon than there is the primary carbon, which means that this carbon is more electrophilic. It's more prone to nucleophilic attack. The nucleophile is Br-. And a second reason that this is the major product formed, the higher energy product, the 1,2 product is the major product, is because of the proximity of the Br- to the secondary carbocation. It's closer to the secondary carbocation than it is to the primary carbocation. Remember, H and Br are associated with each other, so as H plus starts to form a bond with the carbon-carbon double bond of the diene, the Br- is hanging around over here, closer to the carbon number 2 than it is to carbon number 4. So this is called the proximity effect. And let's look on the next slide for evidence to show that this is a real effect. In 1979, some scientists at Case Western Reserve came up with an experiment that demonstrates this proximity effect. They took this diene and they treated it with DCl, and they ended up first with the formation of this carbocation. If they used HCl, they would have obtained a carbocation that had two identical resonance structures. So by using DCl, they end up with a carbocation that actually has two different resonance structures because of this deuterium label. Both of these, regardless of the presence of the deuterium, are of roughly equal stability. They're both secondary allylic carbocations. If there was no proximity effect, you would expect at low temperature to obtain a 50-50 mixture of the products resulting from chloride attacking this carbon, number 2, and the chloride attacking this carbon, number 4. So that means that the 1,2 and the 1,4 products, you would get a 50-50 mixture. But when they carried this reaction out at minus 78 degrees, they actually obtained about 75% of the 1,2 product. That's the kinetic product. And they ended up with 25% of the 1,4 addition product. So this is a real effect. Notice that in this case over here, the positive charge and the chlorine are much closer to each other than in this case over here. This leads to the 1,2 product. This would lead to the 1,4 product. So the proximity effect is apparently a real effect. When you run this reaction at higher temperature, 40 degrees, you allow the system to come to equilibrium. You're providing enough energy to the system that the reaction goes to equilibrium, and as you would expect, the more stable product predominates, the 1,4 addition product. Even though you might have a significant number of molecules of the 1,2 addition product forming right away at the beginning of the reaction, this is a reversible reaction. Even though this forms, you could break this carbon-bromine bond, reform the carbocation, which could then react at the primary carbocation, primary allylic carbocation carbon to form the more stable thermodynamic product. Therefore, at low temperature, the kinetic product would be favored, and at higher temperature, when the system goes to equilibrium, the more stable or thermodynamic product would predominate. We can look at the kinetic versus thermodynamic control of this reaction also by examining the reaction energy profiles that lead to the 1,2 or 1,4 addition products, the kinetic and thermodynamic products. At low temperature, when there's not a lot of energy in the system, the reaction pathway, again, there's two competing pathways. We can either go in this direction or in this direction. This direction leads to the thermodynamic product. This leads to the kinetic product. When there's not enough energy in the system to overcome both activation barriers, both activation energies. The path that has the lowest activation energy is going to be the major path. The reaction is trying to go up this hill. It's a much steeper hill. This is a smaller hill. So therefore, at lower temperature, when you have maybe just enough energy to overcome this smaller activation energy, most of the reaction is going to take the pathway to form the 1,2 product. So under kinetic control, you're interested in which of the two paths has the lowest activation energy. When you apply enough heat to the system to overcome all activation barriers, so in this case we have two, then we're interested in not which product forms fastest, but we're interested in which is the most stable product. In this case, the 1,4 addition product is the thermodynamic product. So therefore, even though a lot of reaction might take this pathway at the very beginning, this is reversible. Remember, you can also break this carbon-bromine bond to reform the allylic cation. And again, if you have enough energy in the system, all activation barriers will be overcome and you will end up with the more stable product being the major product formed. So under low temperature conditions, kinetic control, you're interested in the differences in activation energy of the pathways. When it's higher temperature, it's thermodynamic control, and there you're looking at not the activation energy differences, but you're looking at the difference in free energies, the difference in stabilities between the kinetic and the thermodynamic product. Use what you've learned so far to solve this problem. We have a diene treatment that's treated with HBr at 0 degrees. What would be the products and which one would predominate? Well, we have a diene. It's treated with HBr. We are going to protonate it, and then we're going to have to add Br minus to one of the carbons that has a positive charge. There are two possible carbons that we can protonate. Only one is going to protonate to any extent because that leads to the more stable carbocation. If we protonate this carbon, we end up with a secondary carbocation. Notice that this is the carbocation is not conjugated with, it's not next to this double bond. So this is an isolated secondary carbocation. If we protonate this carbon, we end up with an allylic carbocation, which is delocalized. So we dismiss this immediately over here. We're not going to be protonating on this carbon. We're going to be protonating on this carbon. We're going to end up with a delocalized allylic carbocation. So this particular resonant structure, if it's attacked by Br minus, you end up with the 1,2 product. This one, if it's attacked by Br minus, this carbocation is trapped by Br minus, we end up with the 1,4 addition product. All right. Which product is the kinetic product and which product is the thermodynamic product? And this is where we can analyze the structures, and we'll find out that the 1,2 product is the kinetic product and the 1,4 product is the thermodynamic product in this case. Why is that? Well, why is this the kinetic product? Well, first of all, we talked about the proximity effect. Notice that the Br minus nucleophile is closer to the carbocation on carbon number 2 than it is the one on carbon number 4. So proximity effect would say that this would be the kinetic product. On top of that, we have other structural features, differences between these two that will allow us to determine which is the thermodynamic product. We know that this molecule has a tertiary allylic carbon-bromine bond, and this has a secondary allylic. Well, it's much easier to break this bond than it is to break this bond because this is a tertiary carbon and that's a secondary carbon. In addition, the 1,4 product is a tetrasubstituted double bond, and the 1,2 product has a trisubstituted double bond. So this is more stable. So this is overall thermodynamically more stable. And these are the two products that we form. The next question is which one will predominate? All right, this is at low temperature. All right, it's not as low as minus 78 degrees, I grant you, but it's still a low temperature. And at low temperature, that's non-equilibrium conditions. And under low temperature non-equilibrium conditions, the kinetic product should predominate. We're not asking for numbers here, but just what would be the major and what would be the minor. So this would be the major product because it's the kinetic product. The activation energy leading to this product would be lower than leading to this product. If you did heat this up, then the thermodynamic product would predominate.